And in the meantime, we can probably get started with the first talk of the day by Hongin Luo. Um, so I can already give introduction of Hongin. Um, he's from MIT and subconscious.dev. Is that a startup? Cool. Yeah. So I'm super excited to have someone who's in the academic activities as well as startup activities. That is very, very interesting. And I'm looking forward to your talk on beyond context limits, subconscious threats for long horizon reasoning. hmm So there's also subconscious in the title as well. So I'm looking forward to what you have to say on this topic.
Yeah. Thank you for inviting, and also thank you for the nice introduction. I will go ahead, jump in the slides, and um give more introduction about the work and myself. So uh quickly about myself. I got PhD from MIT and stayed there as a research scientist, and recently working on this MIT spin-off startup company working on both model training and the serving system for this agentic model. The core problem we want to solve is when the model is challenged by the context limit, it has efficiency problem and performance degrades. How do we get rid of those challenges? So in today's talk, I will first introduce our motivation and um, our concepts on working memory, the previous research work called thread, and the team thread inference model. And we'll also cover the design like conceptions about the team run inference engine and share some experiments from the paper and also our latest discoveries. So firstly, why we wanted to do this? So um, I think earlier this year or late last year, I tried to build some agent myself using the those very hard agent frameworks. But I figured out it's extremely complicated if I want to adapt the agent to corner cases where it does not work. That becomes extremely complicated, and I figured out if I want to solve all the problems, I probably need to spend another year working on writing prompts and new workflows for every corner case. That is simply very painful. So that made me think in 2019 when I was writing my like PhD papers, I've been training up the BERT models and GPT-2 models together to put together an AI system. But as of today, we are training like GPT, Gemini up for newer agent systems. The capability of the language models has evolved so much, but the agent or AI app dev flow is as complicated as before. So that is not natural. And the second problem is redundant computation. For most AI systems or AI agents, when it comes to multi-turn user agent interaction or multi-turn tool calling, we usually will collect the tool, for example, the tool parameters from the server side for the tool ourselves and dump the entire context into the language model again. So the cost will take off very soon. And because the tool response can be very long context, then you will soon like explode the context window of the language model. And that will cause, number one, it will make the cost take off. Number two, will cause long context hallucination problem, etc. So that has made the agent development very challenging. So um, the last motivation is that I have been exploring if there's any architecture between transformer and recurrent neural network. So transformer computes attention over all the input tokens, and recurrent neural network just maintain a limited space. they both have pros and cons, and I have been exploring if there is a like a way to compute attention, not on all the tokens, but also it's more expressive than a fixed length state. So all this motivation made us think about the concept of working memory. So as a as a uh, as a mechanism in human perception, we do not keep all the details of our perceptions and memories in our like on top of our mind. So when I'm picking up something, I only care about my goal, but I do not like consciously control my muscle, something like that. So that's working memory. So we prune unnecessary details from that reasoning process. Only keep the important stuff on top of our conscious, and that will help us like focus on the right thing to accomplish a task. So we wanted to attempted to borrow this concept into the development of agents. And this thinking process now has a better name, context engineering. But this is what we have been thinking about last year when we produced the first attempt called Thread. So basically, Thread is similar to uh, the recursion of thought reasoning pipeline, except for it does not maintain the context state. So on the right side is a general it's a rough like illustration for uh thread. So when thread gets an input task, it recursively decomposes subtask in a way that uh since I need to solve this task like thread zero, I need to do something first. So in this manner, thread uh, will auto-regressively output subtask instructions. But the problem of thread is each subtask instruction is handled independently, meaning thread does not maintain a global memory that limits its performance. As a result, we had to build task-specific prompting for more than 4,000 tokens because the structure is defined by some special tokens, and we want language models to learn it. So this setup, number one, it can get some performance improvement on a bunch of agentic tasks like uh, browser use and deep research or even some robotics tasks. But it's very complicated for deployment. So this work when we train the thread inference model, namely TIM, we wanted to solve the deployment problem. Instead of having special tokens to control the structure, we control the structure using JSON dictionaries. Now, the recursive reasoning structure is a recursive JSON object. And secondly, we managed to have state tracking or a shared global context for each subtask. So it does not suffer information loss problem. And GAN model is trained on a synthetic dataset of more than 16,000 tools. So hopefully it's task general, and but at least it's much more task general than the thread framework. And lastly is the team model powered by our team run system enables server-side tool calling. So if the tool is called locally for developers have to dump the tool responses again and again to the server, which will cost the redundant cost and payment. But if the tool is called on the server, then we have a way to significantly improve the throughput of the agent that calls external tools. So this talk will roughly follow the improvements we have done. The first the first thing is probably dive a little more into the JSON generations. So I believe the audience are familiar with generating stuff with OpenAI, and hopefully we have tried generating like grammarly correct JSON dictionaries. So the basic way to define JSON project is having a identic class, for example, in Python, and you give it the fields and the data type of each field, and then the language model can generate a dictionary with exact field and the data types. But the trick here is if we want to generate recursive JSON dictionaries, we can just refer to the class itself. Um, so it's interesting that in other frontier language model systems, OpenAI gives this documentation saying that you can generate a plain JSON. And Anthropic does not provide this. Anthropic says if you want to generate JSON, you should use the tool call mechanism and give the prompt to the language model. But Gemini actually gave us the documentation about how to generate recursive JSON dictionaries. And that's pretty interesting, maybe indicating the way they train the language models. But anyways, we figured out we can generate JSON with the language with language recursive JSON with language models by this definition, which give us the possibility to generate recursive reasoning chain by defining the recursive structure using in this way. And our object to define the reasoning trace is shown here. We have a So on top of everything, we have a class called a team response. So we have a reasoning chain and we have the final answer. So the reasoning chain borrows the concept of all the reasoning models that will think will spend some compute in generating the thinking trace and then generate the final answer. But instead of generating a unstructured piece of text as a reasoning trace, our reasoning trace is a highly structured reasoning tree, which is a list of task objects. And the task object contains a sort, which is a stepwise reasoning, and optional tool use. And it can generate a subtask list that repeats its own structure. And so it can, so the reasoning trace can dive in two dimensions. One is the depth dimension, one is the like regular chain of thought dimension. And we call this subconscious thread. And we call it subconscious because the subtask list can be pruned out of the KV cache. By doing that, we can save the context window, and we can help the model to really only focusing on the important tokens for further reasoning. And by doing that, we believe it's a more effective way for context engineering. Uh, a little more about tool calling. We tried to decode the MCP style tool calling here. So during generation, the language model will specify the tool name. And so, for example, now we need to use a search tool for something, or we need to use the web scraping tool for something and generate the tool responses. So because this reasoning is highly structural, when the inference engine reads after the inference engine reading the tool name and the tool parameters, it can invoke a tool call immediately and append the tool response after the tool result field. So it will always be a valid JSON dictionary and continue reasoning, going back to the reasoning trace, we defined as task and subtask stuff. So I will show a real example after finishing the slide. But roughly, this is what the generated reasoning trace look like. It's a highly structural reasoning tree. It has a subtask decomposition, and in the subtask list, it can expand the reasoning, just like regular chain of thoughts. Because it's highly structural, we can visualize it into this kind of reasoning trains. Might be more observable than other reasoning models. The fun thing is that when I first saw OpenAI's O1 model, I was complaining, why don't you show us the reasoning trace? We really want to dive into that. But when I saw DeepSeek model, they show the entire reasoning tree. I'm not happy either because there are like thousands of thousands of reasoning tokens, and I really cannot read it. So hopefully in this way, it's more like it's more explainable reasoning than the unstructural reasoning models. Hopefully, and that's how we generate. That's the format of our reasoning traces. Now we're diving into how we do the context pruning and the context management mechanism. Our intuition is very simple. So for regular transformer models, we're attending to all the reasoning tokens. And although there are a bunch of efficient attention mechanisms like linear attention or sparse attention, we are sort of arguing that none of these efficient attention mechanisms is as strong as full attention. But computing full attention is basically it's just too expensive for long horizon tasks. So we propose uh, compute full attention just over a subset of all the tokens. So number one, it's like we do not have the attention mechanism maintains uh, its expression capability, but on the other hand, it's more efficient because we have a way to figure out we have a rule-based mechanism to figure out which tokens are more important for future reasoning. And we do it pruning pruning out the subtasks. So subtask 1 is divided into subtask 1.1 and 1.2. But when we complete the task 1 and move to task 2, we only maintain the thought and the conclusion of task 1. But we prune out the subtask list of task 1 out of the KV cache. By doing that, we probably only keep like a few hundred like tokens for task 1. Even task 1 is extremely complicated, and we can dive into the second step. Um, that's the intuition, and our context pruning is a pure like a rule-based approach. There are other context compression mechanisms, like when you generate a bunch of several turns of agent loop, there is another model that summarizes all the conversations, compress the tokens, and feed the new context into the model. But that might take another model, even a stronger model, to summarize the context. I heard some rumor that one of the frontier lab is they have a dedicated model trained for context compression, and that is and apparently they haven't released that model for developers. So that's why developers are struggling with this context management and context pruning stuff. But anyways, we this is a way this is our approach for context management, and in this paper we are discussing whether it is effective. But uh, sharing more details here, we have we do recursive task decomposition. So when we have four components, thinking is a stepwise reasoning, and we have tool use, subtask list, and the conclusion is the result of every step. So looking at task one, after the thinking process, the model decides we need a subtask list. So it will spawn subtask 1.1, hit another subtask token, and it will generate a subtask list of two tasks. And after wrapping up the two subtasks, it returns to the higher level of the parent thread and continues the reasoning for task 1.2. And after 1.2 is wrapped up, we put the uh, subtask list of task 1.1 into the pruning buffer. So in theory, we can prune this out if we are confident. But in our actual implementation, we keep a buffer for some redundancy to better avoid pruning out necessary information. But when there are two subtask lists being wrapped up, we will prune out the current subtask list in the pruning buffer, and we'll put the new subtask list into the pruning buffer and continue the reasoning. So the assumption here is that the subtask list of 1.1 has been aggregated in the conclusion of subtask 1.1 and 1.2. And um, we implemented this subtask pruning uh, by using the Triton kernels on top of the KV cache. So for batch inference, we can prune out different sections of the KV cache for different um, for different requests without writing a for loop to maintain the efficiency. And that's a that is a subtask pruning mechanism. And the last thing would be tool calling. So we managed to do the tool call on the server side. Um, the goal is basically to number one, simplify the agent development efficiency, and number two is to avoid redundant computation, because anyways, if the inference engine returns the tool parameters, it needs to do like context caching, and when the tool result comes back, it needs to handle like cache hitting or even redundant like pre-filling. But with server-side tool calling, if the tool call is efficient enough, we just make the request stay in the KV cache and wait for the tool response to come back, and without blocking other requests. So by doing that, we saw a significant throughput gain of the language model inference. So this is the ideally we want to with this mechanism we want to give the language models unlimited context, so developers can focus on building agents with one language model call instead of like orchestrating multiple different agents and tools. So we have done several experiments with the model. So we trained a 8B parameter model with gRPO on a synthetic task, and we also have a compound system we call team large, but it's prompting GPT 4.1 using using a like carefully designed prompt, and it mimics the output structure of the small model. The challenge here is that we still have to do step-by-step reasoning with team large, with not end-to-end, because OpenAI or Gemini does not do like the grammar state caching. So, but anyways, we saw that on deep research, team large, the GPT 4.1, which is not a reasoning model, get close performance to DeepSeek R1. And on another task, which is the data common, is one of our internal benchmark that we collaborated with Google on their data commons knowledge graph. So previously we hit the performance with Thread with like 4,000 task specific prompt tokens, and now with team model, we just tell it your team, your helpful assistant, these are the tools you can use, and it can hit the same performance. So our next step on this would be, currently we just have 140 test cases, so we will expand the size of the benchmark to make the performance more reliable. Another attempt we tried is on mass tasks. So we are basically comparing our Team 8B model plus SGLang and the Team 8B model with Team Run. The goal here is to figure out if the context engineering can help improve the reasoning performance. So what we found is that on some complicated tasks like AME and GPQA diamond, pruning context can actually improve the performance, which is surprising to us. So when we started this research, we were mainly thinking about efficiency, but turned out for long reasoning tasks, if we can smartly prune out unnecessary tokens for future reasoning, then the language model can better attend to important context tokens and result in higher performance. So our next step for this is adapt the Team 8B model to the latest open source models that are capable of doing like thinking mode like the latest QM model. And um, and by the way, our Team 8B model is also distilled from GPT 4.1, and the GPT 4.1 performance on AIME is roughly between 30 to 40. So it achieves a similar performance. And lastly is about the efficiency. On the left plot, we compare Timron with SGLang under different pruning buffer size. So we show that when the pruning buffer size is 1 or 2, Timron has better like throughput. But if the pruning buffer size is too large, then Timron is basically not pruning out anything, but has extra like overhead for managing the context. And but all the experiment we results we got before was using 2 as the pruning buffer size, meaning that we can actually achieve better accuracy and throughput than SGLang. The right side plot is comparing the throughput against number of tool calls we have. So if we don't do server side tool calling, then it's the blue curve. With the number of tool calls increase, the throughput would drop rapidly. But with context pruning plus server-side tool call, because we saved the context, we made the attention computation more efficient, and also we do not have to go through the context caching and cache hitting. Then the overall throughput is much better when you have multiple tool runs. And lastly, our model is open source and the system is live. And yeah, I think it's 30 minutes. And thank you for listening. If we have extra time, I can show a live example. But the model from the MIT mascot, which is a beaver.
Super good. Thank you so much for your presentation. And yes, we do have time for Q&A. It was originally planned for Q&A and talk together in 30 minutes, but now that there's no speaker for the second part, fortunately, we can use the full hour for discussing about your work and your startup. So the audience is, if you have any question, you can post question on Slack, or you can also raise your hand. And I can also promote you as a panelist, and you can also directly ask questions using your voice. In the meantime, I have tons of questions, so I can probably go ahead and just let me know whenever anyone has any question. So I'm also quite curious about the startup itself, because I don't know how much I can ask and how much you can answer, but just feel free to say, oh, no, I cannot talk about that later on. So I guess the first question is, was this idea thread a paper in the first place? And did the paper develop into a startup eventually?
Um, I think short answer is yes. So we did the thread paper last year, and I think the process is we had a thread paper last year in middle of like May 2024, and then I had the idea of building like a data engineering
Mhm.
agent, and I basically found many like very hot agent frameworks not being helpful for me to build that agent, and I revisited the thread pipeline and figure out the thread pipeline can help me build that agent. But thread is just too difficult to deploy and have a bunch of limitations that I feel I can solve. That involved in the that involved in the new team model. And after observing the good capability of the team model, number one is does like automatic context engineering, and number two is it can basically call tools by itself, which is pretty amazing. And I reached out to a bunch of technical people on LinkedIn, like the engineers in other like startups, and the feedback I got was automatic context engineering is will be very helpful. So and I figured I thought could be a good startup opportunity. So that's the process. That's the history.
Mhm. Thanks a lot for sharing the story. In the meantime, there's one audience member who's raising the hand. I wish to ask them if they want to step up as a moderator, or do you want to type in the question? It's up to you. Or can they say that somehow? Or I can allow them to talk if that's all right. Hi, Raja or Raya.
Yeah, this is Raja actually. Can you guys hear me?
Yes, I can hear
Yes.
you very
Yeah,
well. Thank
yeah,
you.
yeah. Perfect. Thank you guys for doing this. This is awesome. Thank you for your time for presenting this. Had a couple of questions about the buffer size of the model and how you guys subtask it. Um, I saw on the slide that that your suggestion would be to take a task and then have it as a subtask. So what happens when a task does not complete within the buffered space, right? What if it fails? And how does the model recover from that point? So that's the one question. The second question is, so when you guys split the task, how do you guys assign a verification for it, right? Like, how do you know that a task is completed before going back to the parent?
That's a great question. So, yeah, I think I can merge the answers. So, short answer is we actually don't know. The model decides itself. So the entire reasoning trace is generated by the model auto regressively without any pre predefined verification or split mechanisms. So it's just the model. Let me go to another slide. It's just the model decoding adjacent object like this. So after decoding the comma, the model decodes a subtask, and then the model knows, oh, here is the subtask. I start divide stuff. And um, so question number one is how do we know the maybe is how do we know the subtask is completed and what happens if it goes wrong? We do not handle it manually. If it goes wrong, the model will read it, and the model will like either extend reasoning steps in the same context list to fix that, or it will spawn a new subtask, like subtask in subtask to fix that problem. Or the model will generate a conclusion saying, this is impossible, I'll give up. And it will go back to the parent thread. The behavior is like either decided by the model itself, or we can tell the model in the prompt saying, if you try something, if you try some tool and it fails, you need to try other tool instead, and the model will follow the instruction. So that's how the model handles like exceptions and errors. And for completion verification, we didn't do that. The model does it itself. The model will read the conclusion of the previous step, and the model will automatically decide if the model needs to like generate the end of the subtask and go back to the parent subtask list. And the model can do this because we trained the model with GRPO on some synthetic deep research and the math tasks to improve the performance. The model learned the skill for when to spawn subtask like uh and when to prune its context.
Perfect. Thank you, guys. Appreciate it.
Yeah, thank you for the question.
Thanks. I have a follow-up question on this. Um, do you think so? One of the possibilities people talk about when you're working with an agentic system, like multi-agent system, or when you have multiple like hierarchies of tasks, is to introduce the concept of uncertainty, right? So when you complete a task, maybe the subtask can come with this measure of how certain you are about the answer, or yeah, so maybe it fails in a way that, okay, it's super obvious that it failed, but it can also be like, okay, I think I'm right and I'm giving you this answer, but it actually is wrong, right? So do you think any developments in the uncertainty estimation could help with kind of reducing this problem, and whether you're looking into this?
Yeah, that's a very insightful question. The use cases we are currently dealing with, I guess the most errors we run into are probably engineering problems. Like when we call a tool, but that tool is doing feeding back unexpected stuff. The model needs to recover from there and figure out what to do next. But in terms of the model is super confident, maybe, but in the case that the model does not encounter external error signals, it just like secretly go wrong in a mass reading stuff. We haven't dealt with that yet. Doing reinforcement learning, the model will tell us like, wait, this actually does not work. It will try something else. Um, that happens sometime, but that's not a guaranteed behavior. But I do believe uncertainty is a very important thing in reasoning. I believe there were papers on doing reasoning with beam search. For us, we're considering doing parallel inference. So when it hits some subtask and the subtask it might be very challenging, we might split the sub we might like spawn multiple instead of one subtask list. And those subtask lists could potentially inference at the same time. And after they all conclude, we could figure out the uncertainty of each one and pick one of them to merge into the main thread. So that could be a very interesting way to improve the reasoning of thread model.
Yeah, thanks a lot. Any other question? Otherwise, I have some more questions about the company itself as well. So you said you open source this, but also on the company page, I see business model for using the agents on your based on your architecture. So I'm wondering about your business model, if you can share it.
Yeah, we are currently super early, and
Hmm.
the business model we are currently adopting is basically we learn from others. Uh, so we are currently mostly doing the API by API usage. So we host the model, and users can call the model and pay for number of tokens. The benefit is we don't charge for cache tokens. So if you call like a call in a one agent loop, you need to call 10 tools. Probably for OpenAI, you need to keep paying for context tokens. Even they do discount for cache tokens. But with us, we don't charge for cache tokens because because of the algorithm, we actually do not do the cache hitting thing. So the business model is mainly by token.
Okay, thanks a lot. And in the open sourced code, you open source everything, like all the architectural components to kind of engineer this kind of a token saving system, or how do you call this exactly? Token pruning, or context engineering in general, with your algorithm, right?
Actually, we only open sourced the model
Oh,
for
I
like
see.
a
Mhm.
research research purpose. But we didn't open source the underlying serving system.
Mhm.
One of the reasons is just it's not perfect for now, and we're keep improving it.
I see. Yeah, that's an interesting story for sure. Um, I also wonder about sort of the roadmap for the
Mhm.
product, if you can share it. Like, so for now, you seem to have yeah, you said it's not complete and perfect yet, but still, it's kind of a working system which gives you benefits like values in terms of
Mhm.
reduced number of tokens and cost at a similar or even better performances, right? So I'm wondering what next you think you have in mind.
Yeah, we are still exploring. So because we are providing a model, it's definitely not exciting to compete against frontier labs. So we are trying to well, so our roadmap would be we are going to make our like serving system more stable and robust. And secondly, we are trying to find a use case where the agentic task is really very long horizon, involving very complicated tool use, and also the developers are not experts in building agents. Actually, I wonder who would be the expert in building agents. Agent, the concept of agent is just here for 1 year. So no one knows how to do the context pruning stuff. But we're looking for long horizon tasks and hopefully train a bigger model, uh, like 30B-ish model on that task and get good performance and and perhaps dive into that vertical. So yeah, I think that's a rough roadmap, and honestly, we're still exploring.
I think there are a lot of labs trying to kind of improve their models themselves, but not so much on kind of improving the context engineering. Maybe you know some more, and but I feel like well, it's more like I don't see much of the comparison of the context engineering itself, rather than comparing the models themselves. Because we are also doing some literature survey on the space of kind of system engineering for agentic, like multi-agent systems, how to kind of put them, how to prompt them to kind of communicate with each other. And I think there's no standard or there's no kind of quantitative analysis of which way is better than the others. Um, and I think your proposal is a very strong candidate here, which is going to win much of the other ways to kind of do context engineering because you're touching upon something that is quite critical and an easy, I mean, easy as in like, yeah, you don't need to develop a new model or something, right? So easy gains in the trade-off between performance and cost. Although engineering, you said, is quite involved here. Um, so um, I think this is an interesting direction. And I guess the main question that I have is whether um, you're expecting more people to compete in the domain of context engineering in the future. Like instead of competing against the other models themselves, do you think there will be or there should be more work on kind of comparing how you arrange the agents and how you prompt them?
Yeah, yeah. That's a very deep question. So our approach or our positioning is we advertise ourselves as a neural version of, for example, LangChain. So we like burn LangChain into a model, and that model is hopefully it's a model, but it's actually a model that helps you call other tools and even call other models for building agents.
Mm.
And but definitely there will be a bunch of agent frameworks competing each other on helping people build agents, and that help includes context engineering. And by the way, in response to the question in the QA section, the the pricing of our model is for our small model is a 8B model pricing. We match the price of a GPT-4 mini. And for the large compound model, the pricing is same as GPT 4.1 because we are prompting GPT 4.1 there. But we do not charge for cached tokens. But in the longer term, we want to replace our large model with actually a smaller model that is cheaper than GPT 4.1 uh, to help to be that neural, we can call that a neural agent framework um, to help people build agents uh, more easily. So use cases we have encountered is that there are many big companies, like traditional tech companies, trying to become AI native. So what they are basically doing is that they are building MCPs for each one of their internal tools. But after building like 200, 300 MCPs, they actually do not know how to build an agent on top of it because it's like sounds impossible for me to orchestrate 200 tools in one agent loop. But they could be using our model, just dump the dump the dump the tool descriptions into this one model API, and the model figure out the agent, figure out the context management and tool orchestration by itself.
Yeah. And I remember there was another person raising hand. If you wish to ask question, please step up, and I'll promote you as a panelist. Yeah. Otherwise, I also have some questions about connections to memory. Like you mentioned RNN at the beginning, right? And having more persistent structure you can talk to uh, as you generate the tokens. Um, so I haven't. So I probably missed the part where you talked about the relationship between RNNs and your structure. So I was actually wondering if you are kind of moving into the direction of memory networks in the future. Um, so do you have any comments on this?
Uh, I'm I'm not expert in the neural network architecture world. So when I say something between RN and a transformer, it's on a very high level. It's a very high level analogy that the main point is transformer has to look at all the input tokens, but RN only keeps a very limited size of state.
Mhm.
Something between it is more efficient than looking at all the tokens, but is also more expressive than only keep a fixed length state. And that entails we need a transformer model that can smartly pick the correct tokens to look at. Um, another stream of another stream of research is probably the mainstream, arguably, is sparse attention. Keep training the model, keep training the sparse attention until the sparse attention can attend to the correct tokens. Um, that would be too expensive for us, and we still have to wait and believe that a good sparse attention model will come in 2 years. But that won't help us building agent today. So today the approach we use is having the recursive structural reasoning trace, recursively task decomposition frameworks, and do the context pruning that is that help us figure out which tokens are more important. So arguably, our approach is like task hierarchy aware sparse attention.
Mm-hmm. Mm-hmm. Interesting. Yeah. Although I don't know so much about this architectural differences here and there. But thanks for sharing insight here. Cool. Maybe final question from my side. Do you think there's any upper limit on how much you can achieve in terms of cost, if cost performance trade-off?
Uh, yeah, I might have crazy ideas on this, but happy to share. Um, I think traditionally, cost there is always a cost and trade-off, cost and efficiency trade-off. Uh, but my intuition with this might be wrong. Is structural reasoning instead of unstructured reasoning might achieve both better efficiency and better performance. Because number one, we are pruning out tokens from the KV cache. So attention computation will be much cheaper. And secondly, because we do that, the model can attend to important context more easily. So the hope here would be develop something that is both much more efficient and much more capable than uh, existing systems.
Mhm. Thanks. I'm also just wondering if there's any theoretical upper bound on how much you can get better, because I guess in order to accomplish some task anyways, you need some minimal information to do this.
Mm-hmm.
I don't know how to formalize this idea, but I guess in the usual kind of task completion in chain, there are some redundancies, obvious redundancies, and you can kind of get rid of these. But also, you
Mm-hmm.
cannot remove everything, right? Because if you remove everything, then
No.
the task becomes ill-defined, um, and then you're going to lose performance too much. So I wonder if there can be any kind of theoretical study on this to kind of know, okay, we are hitting, let's say, 80% of what is possible, and the remaining 20% we need to address. Or yeah, I wish there to be some kind of way to gauge how far we are from the theoretical kind of best case scenario.
Yeah, that's a
It's a
that's a
very
good
difficult
problem to
question.
think about.
Yeah,
I
that's a paper in its own.
oh yeah, I'm not familiar with theory stuff.
Yeah, but just wondering because you have, yeah, maybe you have some gut feelings of, okay, maybe if we do a little bit more engineering here, we're gonna get a lot better results, or you feel like, oh, we are probably hitting saturation point, and yeah, so which one is the case in your personal experience?
Um, not sure if I'm asking the question, but my intuition is that if we want to encode millions of tokens with one embedding, that's definitely too much to encode.
Mm,
So I guess the frontier labs are keep trying training models that handles like 1 million context tokens, 2 million context tokens. Um, I guess it's a race between the model and the complexity of real world tasks. Not sure which one will. Uh, so not sure if the expression capability of the models can surpass the complexity level of real world tasks. If that's possible, then that's probably the AGI they've been hyping about. But otherwise, if the amount of information in real world is always bigger than what the language model can encode, then we probably always need to feed the language model with selective information. And that selection does not agree. So there might be more research work in how to smartly dump helpful information to the language model.
There has to be some selection algorithm as well, for sure.
Mm.
hmm All right, thanks a lot. And actually, we have only 1 minute left, so we should slowly wrap it up and move on to the next session. I wish to thank you again for sharing so much of your personal accounts and the company and the research. It's super interesting. Um, and we have recorded the conversation that we had, and the plan is to put it on YouTube. If you do not wish any of this to be put on the internet in public space, then just let me know, and we'll do what is right for you. The same goes for Raja. Thanks for asking a question. That was super interesting. And you can also opt out if you wish. Let's thank the speaker again and have a nice daytime in your case. Actually, I guess you're in MIT at the moment.
Yeah, US is. Yeah, thank you very much for inviting me and really enjoy the conversation. Also, have a good rest. Have a good week.